So I'm very sorry for disappointing you by not being a robot specialist at all. In fact, my specialty is to work about the brain. And I think one important message I would like to convey here is that we can see a lot of robots that are designed to replace human beats, to replace missing functions in the brain, in the nervous system. But we should not give up on the brain. In some instances, and I know it's not always the case, but in some instances, we can count on the brain plasticity and reorganization to achieve some functions. And one challenge, I think, for neuroscience and robotics as well, is to find appropriate ways to stimulate the brain in the optimal way so that it learns or relearns how to interact with the environment, how to control muscles, etc. So what we do in our group is we, of course, try to understand how the brain controls action, how the normal brain, and we also try to see how this can give rise to medical applications. So basically, the nervous system can be summarized as a black box sometimes. It's not so black here, but with inputs, sensory inputs, and action output, which is the main output from the brain. And if you look at what's happening in the brain, of course, the brain has to integrate sensory signals to build up sensory representations of the world as a way to build spatial maps, which robots need to navigate as well. And also from these maps, they need to compute motor representations, which are motor commands that are needed for both robotic and human navigation, of course. An important feature of the way human controls their action is that as soon as you move, you trigger sensory signals, visual, somesthetic at least, and that implies that these signals are fed back to the nervous system with extremely short latencies within tens of milliseconds. And this can give rise to an online modification of the ongoing motor program. And this property that we call motor flexibility is one of the main things I'd like to emphasize in my talk. And the other one is that once you perform an action, you still get sensory feedback about the results of your action. And this is fed back to several levels of representations in the brain. And this can also be used to trigger another type of a dynamic process, which is called plasticity, with a different time scale. And these two processes, plasticity and flexibility of sensory motor organization, can both be investigated in a way to try to stimulate and enhance rehabilitation of the patients. So that's the kind of the general goal that our group follows. Today I'm going to follow on the use of the motor flexibility, this online flexibility for rehabilitation. So our basic clinical activity is to measure patients' behavior. Here you have a patient with different markers, passive markers on the arm, and this is the way they grasp a glass, this kind of glass here on the left side, with the thumb, the index finger, and this is the wrist trajectory. So we analyze this kind of kinematics, and we always try to take into account the analysis of these kinematics in such a way as to understand or better apprehend the way the brain represents a sensory input and motor output. So it's kind of, we are not so much interested in the biomechanics, but mostly on the brain itself and on the way the brain works about controlling movements. And we do investigate gait analysis, and we do investigate arm movements. Here I'm going to focus on arm movements. Early kinematic analysis that were derived from chronophotography have been raising the question about whether when you move your arm to grasp a glass, whether you control serially, in parallel, how much link there is between the transport component and the grasp component. And due to detailed kinematic analysis, Untitled was able to show, and was followed by many other researchers, that you do actually control, the brain controls in parallel, has parallel controllers for apprehension, so that is finger movements, and transport. And I just take this example to make the case that there are important levels of automatized coordination in the way the brain controls action. And this is very important because in rehabilitation, most of the emphasis is usually put on intentional control of action. You always ask the patient to pay attention to moving the hand, etc. And if you do this, it seems that you can recover some intentional control of action, but then it has a lot of cost in terms of paying attention to what the patient is doing. For example, here, you have the representation of a patient that was followed during 2 years, and you can see for his paretic arm that in the beginning he was not able to differentiate between movements crossing the midline and movements towards the same side of the shoulder, which basically implies that on the one hand he's moving with a single joint movement, elbow, and on the other side he's moving with coordinating the elbow and the shoulder. Learning to coordinate these two joints take a long time. You can see over the course of these 2 years that the patient needed more than 100 days to learn this thing. So it has an enormous cost to relearn this coordination, and in many patients this is not recovered, and you can see that the patients are moving joints like one by one, like early stage robots. This brings me to address a question that we have investigated a lot in Lyon, which taps about the way that we see the interaction between vision and action. Our intuitive view of vision and action that dates back to, for example, this Descartes, the picture that is from 1662, give the idea that when you produce an action, you always have to be conscious of what you do and perceive first, etc. In fact, what neuroscience has demonstrated is that you have parallel pathways in the brain, and that you don't always need to be conscious of things, you don't always need to have intentions to be able to move, but your brain has lots of internal robots or automatic pilots that can drive some actions. So I want to exemplify here how this works. Very simply here on this slide, you have a hand here and a target, and the hand can move to the target easily. This is another example, but now what happens is the target moves during the movement, then the hand can reorganize, the brain can reorganize the initially planned trajectory to give rise to a movement that is surprisingly characterized by no increase in movement time. That means that these corrections are embedded in the planning of the movement itself. So these motor corrections not only are embedded and don't cost time, but they also can happen very quickly. Imagine a situation where subjects have to move towards this target here. When they start to move, you can trigger a jump of this target. And the jump can be using laboratory tricks. You can make this jump such as it is consciously detected or not by the subject. And even when it is not consciously detected by the subject, you can see that the hand reorganizes the trajectory towards the secondary location of the target here. So you don't need to be conscious and aware and have any intention for your hand to follow a target. And what is interesting is that the latency of these corrections is extremely fast. It takes only less than 100 milliseconds for your hand to reorganize the trajectory when the object jumps. So here is another way to investigate this. When we confront this in normal subjects and patients with parietal lobe the lesions, that is exemplified here. This is a torque motor that is holding an object here, and this object can be moved to here or to there. It can be represented in several locations, and the object can move at the onset of the subject movement or the patient movement. When the object doesn't jump, controls have straight trajectories, straightly curved trajectories from the starting point to the positions, and the velocity profile are like this. In the patient, you find exactly the same kind of velocity profile with a single bump, which shows that the patient has no problem with moving to stationary objects. But now, if you have the object jump from C to D at the onset of the movement, you can see that it takes 100 milliseconds to reorganize the movement, but the movement ends up at this location. And you can see here, in this case, a very tiny increase of movement time. And now if you look at the patients with lesion in the parietal lobe, you see that they are fully unable to do this. That means they have to grow to the first object, close the fingers, and then plan another movement. That implies that these patients have lost their automatic pilot for their hand. So we are able to study, to describe this automatic pilot and locate where functions in the brain imply that this automatic pilot is implemented. So this automatic pilot lies in the parietal lobe, or at least the parietal lobe is involved crucially in this automatic piloting of your hand. So now if you look at the brain network, driving information from the input, V1, visual input, M1, motor output. Of course, this kind of subway map is difficult to follow, but overall, physiological properties and anatomical properties of this network are such that you have different ways to reach the output from the input, and you can discriminate between a fast and a slow tracks to reach the output. And so you can use your slow intentional control, or you can use fast intentional control. And usually you have to coordinate the two systems so that they do the same thing at the same time, of course. So these two systems can be recruited independently, but you have to use them naturally at the same time. You use the two of them at the same time. And again, what I want to say is that traditionally rehabilitation emphasizes mostly the intentional control of the movement. So what about we try to stimulate automatism, the automatic pilot, to boost motor recovery? Here is a proof of concept experiment where we tested 5 motor deficit patients with this kind of robotic table that we call robotable, where magnets are moved under the surface and they can move the objects at the surface of the table. And you see the object is jumping when the patient starts to move. And the idea is that instead of focusing only on the intentional aspect of controlling the movement, we combine this initial intention that the patient has to have with a sense of emergency and try to trigger the automatic pilot in the brain, hoping that using this additional source of stimulation for the motor system will facilitate the patient's recovery and will facilitate the recovery of natural coordination between joints. And an additional thing is that there is less attentional effort for the patient because there is less intention involved, so things come more smoothly and more naturally for the patient. So very quickly about this, that's just the design of the experiment, just very normal procedure. You do pre-test, you do a training and a control condition, and then you do post-test 1, post-test 2, and you have clinical analysis of the motor deficit, kinematic analysis of the motor deficit. So these two evaluations can be compared to the pre-test. And basically, we used simultaneously 3 types of stimulating the brain automatic pilot. One is to stimulate movement initiation. In this condition, the object is placed next to the hand, and suddenly the object starts to escape from the patient, and the patient has to grasp it before the object is too far. So this is to stimulate the sense of emergency. The other one is emergency rescuing condition, where there is a glass here, and then there is a projectile, a ball coming, that is going to knock off the glass, and the patient has to save the glass before the ball knocks the glass. And the last one is a last-minute correction, which is the automatic pilot that I've just shown you before, where the object jumps. For example, here, this is the escape situation, where you can see the patient catching the ball before it moves too far. And this is the rescue situation. The projectile arrives, and the patient has to save the object by pushing on it when they have no finger movement, or grasp it away when they have finger movements as well. So what can we see in these conditions? If we have these groups of 5 subjects, you can see that the patients who had only the intentional training had this kind of more stationary curve with less recovery than the patients who were following this automatic pilot stimulation. And this is also true for kinematic analysis, where you can see a stable performance in the patients who has followed only the stationary object training, whereas reduction, improvement of performance here in blue in the patients who followed the automatic pilot stimulation. I think I forgot to mention that the training was 6 sessions scattered over 10 days. So the take-home message I want to propose for you here is that the brain body contains robots too, if I can use the word robots here, and their impact for rehabilitation should not be overlooked. Training the automatic pilot together with intentional control, which is done traditionally, enhances the patient's recovery in the short term. And further studies, of course, will be needed to investigate what is the longer-term impact of this kind of procedure and how much benefit we can get, especially in terms of the quality of the movement recovered by the patients. So, of course, I want to propose that maybe slightly overlooked and neglected area of robotic development is to facilitate rehabilitation and provide assistance for rehabilitation. Once again, one thing I want to emphasize in the talk is that we tend to always to focus on intentional control, as if still, like Descartes was thinking, we have like a divine spirit somewhere that is controlling everything below, but there is a lot of autonomous life going on in our sensory motor interaction, and this life has to be stimulated to get most of the benefit of the training. So this apparent hierarchy between cognitive representations and sensory motor representation is also hiding the truth, which is that sensory motor processes, just like is very much known for the development of children, have a huge impact on structuring the whole way the brains conceive of the world and interacting with the world. So my proposal, on the last slide, I want to say, like, we have lots of examples where robots do things for yourself. And that means that robots are external resources and you use active and intelligent ortheses, like we have seen brilliant examples in the previous talks. Now, what I think is another challenge in rehabilitation is robots are also needed to teach patients how to relearn to do what they want to do. Of course, when resources are available, when muscles, bones, and brains and neurons are there to do the job. So the idea is to stimulate brain resources and support and enhance recovery instead of simply try to leave the brain, give up on the brain and focus on replacing the brain, basically. In my view, when you want to rehabilitate patients following this track, you should follow two main steps. The first step is to make an invitation to this system. That is, for example, if you take the example of an exoskeleton, you can imagine that this exoskeleton is providing the paralytic limb, the paralyzed limb, with a kind of tunnel where movement is highly facilitated with very low viscosity, maybe negative viscosity if it is possible. And to know exactly what kind of motor command and what kind of coordination patterns you need to inject in this arm to facilitate this movement and invite the sensory motor action to take place again, I think you need to record on the other arm what are the natural properties of the coordination in the subject, because every one of us has different coordination patterns naturally. And then once you achieve this, once you start firing neurons between sensory and motor input, when you start activating the system, then you can think of gradually reducing this facilitation. And at the second stage, you can even think of making this natural movement harder so that you kind of strengthen this kind of muscle training, but the difference with muscle training is that it is neuromuscular training, so you train the whole system, the brain and the muscles, to relearn to produce the kind of patterns that are natural in the patient. And then you can think of having sessions where the patient comes at distance to relearn or what they have partially forgotten. This is my proposal for today. Thank you very much for your attention.